welcome to Turn the Page, the official podcast of the Syosset Public Library. Hello, welcome to Turn the Page. My name is Ralph Cateau. I'm a librarian at Syosset Public Library, here with Natalie Starkey, author of Fire and Ice. Now, Fire and Ice is not just the name of a Pat Benatar song, but it's the name of this great book that talks about volcanoes. And, well, I'm going to start off, first of all, with saying, welcome, Natalie. Thank you for joining us today.
Hi, thank you so much for having me. It's really exciting to be talking about my new book.
So I'm going to start off the bat with the moon Enceladus, if I'm pronouncing it right, Enceladus. Ice volcanoes. Please tell me about ice volcanoes. That blew my mind. I just sat there kind of like you reading that part over and over again. That was amazing.
I know. So this, it was part of the reason I wanted to write the book, really, because I think a lot of people know a lot about volcanoes on Earth. You know, we see them in the media, they erupt a lot, they cause havoc all over the place, but they're definitely always kind of hot things. You know, there's hot lava or ash, exploded rock that comes out of them. And I think what a lot of people don't realize is that way back now, we're talking about the 1970s and 80s, we sent out these spacecraft to investigate the outer solar system, of which we knew really little about at the time. We'd never been to most of the outer planets or their moons, and we sort of assumed that they'd all be just cold and dead because we think, okay, frozen lumps of ice, they're not going to be doing anything. But as soon as we got out there, we started to see that, it was completely wrong. Our assumptions about the outer solar system were just proved wrong because we started seeing evidence for activity everywhere. And actually the first place we found it was a little moon of Uranus called Triton, and there was activity seen there. But then coming back to Enceladus, as you've asked about, there's different ways to say it. Some people say Enceladus, some people say Enceladus. But this is a moon of Saturn, which is icy on the surface. But actually what we've discovered is that below that icy kind of crust, you've got an ocean world. So it's got basically the same kind of thing that we have on Earth, except it's covered in ice. So we've got salty water sitting below the surface. Now, to have salty water at this distance from the sun, we know there must be some kind of heat inside that world to create that water to keep it liquid. And that was very confusing for scientists at the start because they just didn't understand how something so far from the sun could be generating heat still. And that's part of the mystery of how, we've discovered these volcanic worlds out there, and then the science behind how do we know what's going on there, and how do we discover more about them.
That really, there's something else you mentioned. It was just, I believe in the first, in the preface of the book, that actually, you mentioned how the heat created within the moon keeps a liquid, the oceans there, the liquefied ocean. Inside the core of the Earth is hotter than the sun.
Yeah, so it's crazy, right? So the outer core of our own planet is also liquid, so it kind of churns around, and actually the temperature to keep iron, which it's made of kind of iron and small amounts of other elements in there, but mostly iron, it's over the temperature of the kind of outer surface of the sun, so it's super hot to keep that churning iron happening. Now that heat has actually been in the planet since it formed 4.5 billion years ago, so it's essentially the heat of formation. When you form a planet and a huge object like, the Earth, it's usually formed through collisions of smaller objects. So you might take smaller, what we might call planetesimals, or basically large asteroids. If you take a bunch of asteroids and you collide them together, you can imagine that if this is happening at these kind of crazy speeds that you'd get of stuff orbiting around the sun, there's a lot of kinetic energy that gets transferred to heat. So all that heat that comes from those collisions basically get stored within those planets. And the same happened with Mercury and Venus and Mars and Earth and the moon. They've all had heat inside them from the start. Now, the way they've then evolved over time, over that 4.5 billion years since they formed, then relates to their size, and that controls how quickly they lost that heat. But it also relates to how far they are from the sun, and then it relates to what's in them. So if they have a lot of certain types of elements, they can stay hot for longer. So the Earth has a lot of heat producing elements in its mantle. So you've got the core in the middle, and then you've got this huge volume of the Earth, which is called the mantle. Now it's solid rock, but it essentially flows like it is a liquid, but we shouldn't think of it as a liquid. But it's got these heat producing elements in there, which produce more heat for the Earth. So it basically is just a big hot water bottle. You know, you've just got so much heat within inside the planet. And that is what creates all the activity that we see on our surface, our volcanoes, our earthquakes, everything that we see. And we wouldn't be here without that heat within inside our planet. So life could not be on our planet without it. So when we go out into the solar system, we sort of, if we want to look for life anywhere, well, we need to look for those same things that Earth has. We need to see evidence for heat escaping in terms of volcanoes or some kind of activity happening on the surface. And then we can start to go, okay, could this be a life-giving world, for example?
Wow. Okay. I wish, what I love about these books, especially, and I have to compliment you on the writing, is that you make it flow so easy and make it like almost like a narrative, like a story. And I wish, I'm hoping that more people, this podcast will help more people be aware of like some amazing things that you've written down, and just things, get them curious about what's out there and what's here also, in terms of this. Is, I mean, we all love volcanoes. I mean, when I was a kid, I made one of those projects where you took a Play-Doh and you make a volcano, you put the baking soda and that whole thing. And from then on, it's always been interesting. So, I mean, hearing this occurs so far away and in such a varied different ways, I think is really, people need to know.
I completely agree. And I've done that same experiment when I was younger. I remember ruining my parents' lawn because I did it on the grass, and it completely killed the grass and left a big white patch, and they weren't very happy with me. But I've done it more recently with my daughter, and it's just a great experiment to show, what kind of happens inside a volcano and how material bubbles out the top. But it really only shows you sort of one type of volcano. And that's the funny thing about our planet, because we have so much more varied geology than other planets and moons out in the solar system. So we have a thing called plate tectonics, which a lot of people will be aware of. It's the fact that the kind of outer surface of our Earth or our world is broken into pieces that move around. So that essentially the continents move around in relation to each other. But it's not a smooth process. And this is partly what creates our interesting geology. We get the Himalayas, we get huge mountain chains, and then we get deep trenches in the sea, and then we also get volcanoes and earthquakes. But plate tectonics, as far as we know, only happens on Earth. So Earth is this weird planet. It's the one we know so well, but it is really unique in the fact that we haven't found life anywhere else. We haven't found liquid water on the surface of any other world out there so far. We found it below the surface, but not on it. We haven't found anywhere that is life-giving in the way that we would require it to be. Of course, there are weird types of life out there that could survive in extreme environments, but for humans to survive, there's nowhere else we could survive. So, there's all this talk about going off to explore Mars and the moon and even further into space, but we've got to remember that humans are not adapted to those environments, and without a lot of support, we simply couldn't survive in those places.
Right. I want to sort of start off with a bang as far as some of the bigger points in your book, but I'll go into more. What's your journey? Like, how did you come to be who you are, to study volcanoes and all kinds of cool things, comets and asteroids and things like that? How did that happen?
Yeah, it's been an interesting one. I just got really interested in volcanoes when I was studying for my A-levels. So when I was just kind of before I went to university, I was about 17. And I read this book about a volcano in Colombia. It's called Galerus. And a quite famous geologist, volcanologist, wrote a book about an expedition he'd taken with some other scientists after a conference that they'd been to up to the summit of this volcano to study it in more detail. And unfortunately, there was an eruption that happened at the summit when literally some of them were inside the summit and some were just outside. And it killed some of them, and he got, almost fatally injured. He had life-changing injuries. And the story is just fascinating. It's called Surviving Galerus. It's a bit controversial because scientists since then have come out and said, well, he should have known better. He should have looked at the data and seen that actually the volcano was going to erupt. And so there was a lot of controversy, and there's another book, actually, I think it's called No Apparent Danger, which kind of shows the other side to that story. But I just found the whole thing fascinating that, first of all, that people go up volcanoes to study them and want to understand more about why they erupt and why they would put themselves in danger. to do that. Now, he denies that he thought he was in danger. Obviously, I think I believe him, because I don't think he would have gone up there if he thought he was going to get injured. But it just fascinated me, and I don't consider myself like a risk taker particularly, but I was for some reason fascinated by these volcanoes and wanted to go and study active volcanoes particularly. So I carried on in my studies and studied geology, and then I moved into geochemistry, because that allowed me to analyze the chemistry of the rocks that came from volcanoes. So basically you're picking them apart in a lab and understanding where all those elements that they're made from came from. So within the earth, you can kind of pick apart how those rocks were formed and why that volcano erupts. And then, yes, weirdly, that led me on to space science in a very roundabout kind of way, because the lab instrument I was using to study the volcanic rocks was the same thing that was being used to study some comet and asteroid samples at a different university. So I applied for a job there, and they said, well, you're going to be working on these samples from the Stardust mission, which is a NASA mission to a comet. And I didn't know anything. I really didn't know much about space at the time, but I said, fine, I'll study it. It's all rocks. These are just rocks that formed somewhere else in space, and the Earth is a planet in space after all. It can't be that different. So off I went and started, delved into the world of comets and asteroids and meteorites. And I did some analysis from moon rocks and Martian rocks. It was absolutely fascinating. So I took this deep dive into space, essentially. And then, so that's kind of where this book came from. I originally wrote Catching Stardust, which was my first book about comets and asteroids. And then I moved on because I thought, well, I'm going to go back now and combine all that knowledge with my space knowledge and my original kind of volcano knowledge, and create this new book, Fire and Ice, which I was just really excited to write. But it did take a lot of research, because I've never studied space volcanoes. I've studied them on Earth, but I have studied space a lot. So it was great. I learned so much whilst writing this book, actually, and I got to interview different scientists about their work. And yeah, it's been a really fun journey, actually, of actually just writing the book.
You're talking about the volcanologist who got severely injured like that, and I think you mentioned this also in the book, that that doomed expedition, not expedition, but that it was a group of tourists in New Zealand who also were unfortunately, some of them lost their lives. It's something where, is it really that unpredictable, or are the signs, can it be interpreted different ways, or?
Yeah, so luckily in recent years, meaning kind of the last few decades, we've got a lot better at sort of forecasting when eruptions are going to happen. So we sort of understand individual volcanoes in a lot more detail. So that allows scientists to make sort of forecasts about when they think they're going to erupt. Now, it's very hard to say, it's going to erupt at 10 a.m. on Saturday. That's impossible to do. But what they can do is say something like, this volcano is unrest, it's at unrest now. And so if there's population nearby, they would make the decision to probably evacuate nearby populations. Now, the problem comes when they say, we need to evacuate these towns around the volcano, and then the volcano doesn't erupt, because they are unpredictable. So people sort of lose faith in, the scientists, and they want to go back to their homes, quite rightly, because, they've had to abandon everything. And so scientists and, usually the agencies that work with them have to kind of, toe this fine line between, not doing it too early, but obviously not leaving it too late. And there's been a few really famous examples where it's gone right. Pinatubo is one of the big ones in the Philippines. Mount St. Helens was good. There weren't many people in the local area, but we knew kind of when that was going to happen a little bit, but there were still people in the region that did die in the eruption. And then we've also got the Soufriere Hills in Montserrat, where it's a small Caribbean island. They managed to evacuate nearly everybody off the southern portion of the island, and then the volcano did start erupting for the following kind of 4 years quite heavily. So it's in New Zealand, the opposite happened. So the volcano was sort of, I think, at like a lowish level. They weren't expecting it to do anything big, but the issue with volcanoes is that the closer you are, in more danger you're going to be. So the further away you are, if it has a big eruption, you're not going to, you might feel some ash fall, but you won't probably get killed by that unless you have breathing difficulties. If you're close to a volcano, even a very small eruption can have devastating effects. So this group of tourists were on a volcano tour, and they were right on the island. And so, this relatively small eruption really on a very active volcano was going to be devastating. And so this is the kind of thing that I think sometimes tourists maybe don't realize. They follow the volcano tour because they think, oh, it's safe because this volcano tour is going, it must be fine. They're taking us to this volcano. It won't erupt, they don't erupt very often. But obviously when they do, it can just be awful. So It's a really tricky one. I love that people want to go and visit volcanoes and learn more about them, but actually there's been instances where even just the gases coming out of a volcano have, killed people because, especially if they have lung difficulties in some way, it can be really, really dangerous. And you can't see that happening. You wouldn't even know, the gases were coming out essentially. So they are dangerous, but the more we can study them, quite frankly, we will understand more about them and be able to forecast better when they're going to erupt and, move people away or not let them near it.
Right. A lot of times I think people think that science is like a very a perfect thing where, if this doesn't come true, then we just discredit the whole thing and this is all bunk and this is just hysteria. I think it's even so much, it's a common trope in movies where you'll have the one person who's like, this is bad, it's going to explode. No, that's going to upset the tourists. We can't do that. It's kind of, what's the stereotype? So I think that if people maybe just take a little caution, do you think maybe it's better if you have volcano tours of extinct volcanoes would be better, would be a lot safer?
Yeah, they're not as interesting though, because you don't get all the interesting geology and, so I think one of the most visited volcanoes in the world is Kilauea on Hawaii. And, I've been there and it's relatively safe because, it's the type of volcano it is. It doesn't tend to have really explosive eruptions. So you can be relatively close. You can be on the summit and you can look into the crater lake at the top and you see molten lava. And that's fascinating. And really it is safe. I don't know how many people have died on Kilauea. I think it would be very, very low. And even when it did erupt, quite big style in 2018, a lot of damage was caused to property and everything, but people were fine and they could literally watch the flows going by and stand right next to them. So it really depends. You've kind of got to understand your beast. You've got to know what kind of volcano it does. What's it done in the past? Does it do the big style eruptions or does it kind of flow with lava where you can sort of outrun it essentially? So yeah, it's the more we understand about them, the better.
And like you said before, there were different types. Some are more like that traditional canonical, like mountain type, and some are very flat.
Yeah.
Okay, I see.
So yeah, the canonical ones, I always think of Mount Fuji in Japan because it's like that beautiful, triangular peak, snow-capped mountain. And if it were to erupt, it will go big style. But then I compare that to Kilauea again in Hawaii. It seemed if you drive up to the top of it, you are on a mountain. It's very high, but it's a very low-lying volcano. So it's very wide and it's called a shield volcano. And these are actually the same volcanoes that we get all over the solar system. So the Mars has a massive volcano, the biggest mountain in the solar system, called Olympus Mons, and that's a shield volcano. Just like Hawaii, it's actually just much, much bigger than Kilauea or Mauna Kea or whatever it is. So it's enormous, and you get the same type on Io, which is a tiny moon around Jupiter, and you get the same type on Venus. And so these volcanoes are very, very common. So if we want to understand those on other planets, then, it's best to study the type like we get in Hawaii, because they can tell us a lot more about the ones in space. But yeah, I think the problem you have then in space is that the environment's different. So for example, Mount Olympus Mons is so much larger because Mars is smaller, so it has less gravity. So a mountain can simply grow larger in that environment. And it also doesn't have so much erosion in terms of it hasn't got so much of an atmosphere. So in terms of wearing that mountain away, that doesn't happen as quickly on Mars as it would on Earth. So if you had an eruption on Mars today, it's probably not going to happen because it's pretty much extinct. How would that flow come out? Would it be different because the gravity's less and the pressure's different to that we find on Earth, and it doesn't have the same atmosphere? So, if you throw a load of lava out, what's going to happen to it? Is it going to travel further? Is it going to, be a different density? So that's kind of, all of those things are really hard to understand in space because we're still trying to understand those things on Earth.
What's the primary means, I guess, to study So you mentioned, I think in the I think it was just a talk you had given or a preview for the book on Venus, how Venus is, you can't really see that well, like the visuals are obvious because of the atmosphere, but we think down there there's probably volcanoes on the surface of Venus, but it's hard to even detect it. Can we see some things there right now, or is it getting better, or?
Yeah, so interestingly, NASA have decided to send 2 missions to Venus within the next, I can't remember when they launch, but within the next decade. So suddenly it's been decided that Venus is the planet to be studying. It's always been Mars. Mars has had so many rovers and orbiters sent to it, but now Venus is there. And actually the European Space Agency are also sending a mission there, and I think the Indian Space Agency. So it's going to have tons and tons of information coming back over the next decade or so. But what you can do is mostly study it from orbit. So we've done that a lot with Mars, and we do it a lot with our own planet. You send a satellite into orbit around a planet, and you can then beam back images of its surface. Now on Venus, because it's got this really thick atmosphere of carbon dioxide, you need a radar to see through that. But radar it can penetrate through clouds, and then you see the surface. So you might have seen images of Venus's surface, and it looks absolutely spectacular. It's kind of orange, and you can sort of see these flows that look almost like rivers running across it. Well, they're just lava flows, but massive, massive lava flows, because Venus is about the same size as Earth. So when you kind of get that image in your head and then see these flows across it, and I go and Google some because it's beautiful, they're absolutely massive. So we can see the surface. Now, we've never seen a volcano erupting because we've not studied it in enough detail yet. So these missions that go there maybe, it would be amazing if they did, they may see an eruption happening. But there are other ways to figure out whether a volcano has erupted fairly recently. So some of these missions can look at the composition of the rocks that are currently sitting on the surface. And then they can do some clever science and say, okay, well, there's this particular mineral we've detected on the surface, this particular rock mineral, and actually it wouldn't be there if the volcano had erupted, say, 1 million years ago. The fact it's there now shows us that the volcano must have erupted within the last few weeks, for example. Even though we didn't see it erupt, we can see the evidence of that on the surface. So I think 2 of these missions are actually going to be sending down sort of landers to the surface, but they won't survive very long. They're basically going to be going through the atmosphere and taking measurements as they go, finding out what gases are in that atmosphere, which again can tell us about the volcanoes on the surface. But because Venus is 450 degrees Celsius, it's hot enough to melt lead, and it's got a huge crazy pressure at the surface. Spacecraft don't survive. The Russians or the Soviets sent some spacecraft there back in the, I'm going to say 70s, it might be the 80s. And they lasted just a couple of hours on the surface. So it's a horrible environment, to try and study, but I'm really happy that the space agencies have decided that we need to learn more about it, because I think it's probably still active. And so I'm just waiting to see kind of how active, basically.
Okay. Do you find in explaining these concepts, is it, I want to say come easy for you, but to sort of explain them for the lay reader? Because you're getting, dealing with very technical, very complex subjects, I've always loved science, but what always got me is the math. I was horrible at it, so that's why it kind of kept me from it. But I do like to kind of read about these things just to learn, as much as I can. Do you find that, I don't know, how do you find, in other words, to do that? To take these complex concepts and kind of make them understandable for the lay reader?
Yeah, I've always found it really good to talk through the problems, even if I just talk to myself, that I find a way to explain things, and then I can write it down, or I make notes to try and think about how would I explain this to, a school child, for example, because if we can get it down to that level where we don't assume they have a ton of knowledge, we just assume they know a little bit about lots of things, then I find that's the best way to do it. And I had the same thing, I never enjoyed maths at school that much, but then when I had to start using it in my degrees and actually applying it to real problems in science, and I got to see them, that the numbers related to something, I found that was just so much more interesting. I still found it hard, and I always have found it hard, but I've much more enjoyed using maths when I've got a reason to do it. So when I've got a geochemical equation that I need to solve and find out, the answer to why this rock formed in a certain place, it can allow me to get those answers. So I see where you're coming from. And then, I think a lot of people do struggle with that. But I think in general, when you speak to kids about science, they get turned off science around it happens often around 12 years old. It's very common that kids will either get switched onto science or switched off. And I feel like it's just sometimes the way it's presented at school, that it gets quite dry. And actually, if we were to teach them about chemistry and maths using space volcanoes, well, maybe they'd find it a bit more fascinating. But I think, it's really tricky. And I think during the writing of this book, again, when I was finding new areas that I was researching that I didn't know much about myself, and then I interviewed people. I had to really go back and double check things because, some of the stuff is just so kind of crazy and it's hard to understand because it's not what we're used to. Just like, why is this moon of Neptune, making volcanoes when it's like as far away from the Earth as Pluto, basically. And so I had to go back and try and understand how that heat was generated and then ask them more questions. And I think I've always just been interested to find out stuff. I just like knowing stuff. So that's kind of pushed me on a bit.
You have the curiosity, that helps a lot.
Definitely.
Okay. So you read, your first book is Catching Stardust, and Fire and Ice is coming out shortly. Where else can we find some of your work?
So I mostly do kind of podcasts and things. So I've worked a bit with Star Talk Radio out in New York. And I've also written a planetarium show for the Museum of Natural History in New York at the Hayden Planetarium. So that show actually, it premiered in January 2020. I get my years all confused now with the pandemic, but yeah, just before the pandemic hit. So we had the premiere of that. And then unfortunately, obviously the theatre closed down for quite some time, but it's now open again. And I'm so excited that, audiences can go and see that. It's narrated by Lupita Nyong'o. So I was just, was so excited when I wrote that script and then she read it for us. And it was just, it was kind of like a career highlight for me to have, my script read by an, Oscar winner. So that was a really fun show to write. It was one of the most kind of creative things I've done because I was working with, artistic visualization artists and scientists, and we had to bring together this story about the solar system, which was just so much fun to write. And then I'm hoping to move into writing some children's books actually soon. I'm thinking about different ideas of maybe turning Catching Stardust and Fire and Ice into a kind of highly illustrated kids book in some way to kind of get that across. I've had great feedback from slightly older kids about Catching Stardust, so I know that has appealed to them, kind of 11 plus, let's say. Some really highly interested science kids have really enjoyed it, so I'm pleased that it is appealing to them and that they can understand it. But I do feel like I could write a different version for younger kids, so that's kind of in my ideas at the moment.
Excellent. Yeah, I had seen some of your, actually a couple of your talks on YouTube, and I was on Star Talk, and I thought they were really interesting. Also, the different things you cover about, like, say, water and solar system, and so I'd highly recommend anyone who's listening, if you're interested, go check those out as well. Okay.
Thank you.
Thank you very much, Dr. Starkey, I should say.
Thank you.
Thank you very much for joining us today. It's been a pleasure. I could sit here probably and, fortunately for you, talk all day about this because I find this endlessly fascinating, but I have time constraints. So again, I want to thank you, and I want everybody to who's listening to go and check out both of her books and her work. She's really a great writer, great bringer of science to people that, are not very good at math. So thank you very much. And with that, we're going to turn the page. It's time to close this chapter of Turn the Page. Join us for the next episode.